Black holes are a captivating subject for both space enthusiasts and the general public alike. However, they are also among the most intricate and perplexing concepts in the realm of physics. Countless science fiction films have been created around them, often using black holes to manipulate time in various ways. Imagine entering a coffee shop or a bar and asking a random stranger to explain black holes. They might provide a simplified version, perhaps akin to the movie Interstellar, explaining how time slows down as you approach one. What's less likely is an average person being able to elucidate why time dilates near a black hole and even appears to stop inside it. This video aims to address that. By the end of this video, you should possess a much clearer and simplified grasp of black holes. So, the next time someone in a coffee shop or bar approaches you to discuss black holes, you'll be well equipped to engage in an enlightening conversation. Firstly, it's essential to understand that black holes aren't objects, despite often being portrayed as enormous black spherical objects floating in space. You can't touch them. Rather, they result from the extreme warping of space-time, leading to profound and mind-bending effects on physics. Black holes are so peculiar that without robust explanations and continuous observations corroborating the mathematics, they might be dismissed as mere tools in science fiction. However, they are real, perilous, and can be incredibly massive. While black holes come in various sizes, some are as minuscule as atoms, but these tiny black holes can't maintain their structure. The smallest known black hole that can be is approximately 3 times the mass of our Sun, a unit referred to as solar masses. On the other end of the spectrum, the largest black holes can reach billions of solar masses, capable of enveloping our entire solar system. Ton 618, for instance, is the most massive confirmed black hole, with a staggering 60 billion solar masses. To put this into perspective, that minuscule dot represents our entire solar system. Phoenix A is a theorized black hole. It's estimated to be even larger than Ton 618. It hasn't been officially confirmed. Additional research is required to cement Phoenix A's position atop the black hole hierarchy. Despite variations in size, black holes generally form in one of two ways. Either an excessive amount of material is drawn into a star's core during its collapse, or a neutron star accumulates sufficient material to exceed roughly 2 to 3 solar masses. While some variations exist within these scenarios, all black hole formations fall into one of these two categories. Now, let's delve into the truly bizarre aspects. Why does time seemingly halt within a black hole? One way to visualize the impact of black holes on space is by envisioning an exceptionally vast and profound hole so deep that its bottom is invisible, possibly non-existent. This is a metaphorical representation of what black holes do to the fabric of space. The gravitational force is so concentrated and potent that it creates an extensive depression in space, resembling an endlessly deep pit with a gradual slope. Unfortunately, we can't perceive this spatial dip physically because it exists in a higher fourth dimension, beyond our 3-dimensional perception. To understand this, think of a 2D drawing of a basketball falling. The basketball appears smaller as it moves away and larger as it approaches, giving the illusion of 3D motion within a 2D space. Similarly, when an object moves within a higher fourth-dimensional space, our 3-dimensional perspective doesn't observe changes in the object's dimensions. Instead, we perceive alterations in how it interacts with time. To simplify, imagine a photon of light moving towards this spatial depression in 4 dimensions. In 4 dimensions, you'd witness the photon descending into the dip. In our 3-dimensional world, it would seem as if the light were decelerating because our perspective is confined to a lower dimension, altering our perception of time. To reiterate in simpler terms, from a top-down or 2D perspective, whether it's a light photon or a person entering a black hole, the external observer observes them descending into a 4th-dimensional realm. The speed of light or the object's descent remains constant. However, to the external observer viewing this event in 3 dimensions, it appears as if the entity within the black hole is slowing down. This is how black holes manipulate both space and time. Suppose you were to approach a black hole closely. You'd begin descending into the spatial temporal pit. However, time wouldn't feel any different to you, only the way it appears would change for those distant from the black hole. Thus, the impact of black holes on time is relative. What you experience near a black hole differs from what someone on Earth perceives. To them, it seems like you're slowing down, but to you, It seems like they're accelerating. So, does time slow down near a black hole, or does it eventually stop somewhere inside? Does it merely slow to a point where it seems halted? Once you reach a black hole's event horizon, gravity is so intense that space moves at the speed of light. Consequently, our perception of time appears to halt because light maintains a constant speed. If space moves as swiftly as light, an external observer perceives light as motionless. Beyond the event horizon, the point of no return in black holes, time doesn't exactly stop, it holds. Understand that this concept of time slowing down or holding is all relative. If, hypothetically, you managed to survive crossing a black hole's event horizon, you wouldn't perceive any difference in the passage of time. However, to an external observer, if they could somehow observe you within the black hole, you'd appear frozen in time eternally. All this unfolds because space-time is moving at the speed of light. Remember that this is an overly simplified explanation of an immensely complex topic accompanied by intricate mathematics. The devil, in this case, is indeed in the details, with the black hole itself serving as the enigma. Nevertheless, I hope this has provided you with a somewhat improved comprehension of what black holes are and their profound impact on the universe and space-time. The next time someone engages you in a conversation about interstellar or black holes in general, you'll be equipped with a deeper insight to contribute to the discourse.